Okay, so this is a really good continuous probability question from the 2007 VCA exam. In the Great Fun Amusement Park, there is a small train called Puffing Birdie, which does a circuit of the park. The continuous random variable t, the time in minutes for a circuit to be completed, has a probability function shown here. Sketch the graph of y equals f of t on the axis provided. Alright, we can see that they're both linear lines. We know that the domain is between 10 and 20, and then 20 and 30 for the other line. So let's put those values in. So that means 10's roughly there. Let's say 20's there, and then 30's there somewhere. Okay, for the first line, we can see that it's linear, obviously. And what we can do is we can substitute in the endpoints to just find two values on the line. So for this function here, it's f of, let's say 10 first, equals 1 on 100 times 10 minus 10 equals 0. So we know that this point here is actually an x-axis intercept, which is handy. Alright, the next part we can do is substitute in 20. So let's do that. So it will be f of 20 equals 1 on 100 times 20 minus 10. 20 minus 10 is 10, so it's 1 on 100 times 10, which is 0.1. So at 20, we're going to have an open circle because it's not including 20, but that's not going to matter in a second, as you'll see. And the value is equal to 0.1, not 6.1. 0.1. So we can connect those points up. All right, let's do the next line. Let's do it in a different color just so we can make it clear. All right, f of 20, let's see what that is. Well, it's 1 on 100 times 30 minus 20. If we're substituting in 20 for t, well, that's 1 on 100 times 30 minus 20 is 10, so again, that's 0.1. And it's including the point 20, so we're going to have to shade that in now, so it didn't really matter before. And let's do the last point, so f of 30. You can probably see that it's going to be equal to 0. 1 on 100 times 30 minus 30 equals 1 on 100 times 0. You get it, it's equal to 0. Good, so we can see that this point here is also an x-axis intercept. Looks something like that, and then 0 elsewhere. Well, what does that mean? That just means from here onwards, when it's not inside our domain, when we're not inside 10 and 30 elsewhere or otherwise, our probability density function is 0. Make sure you put those arrows on the end. Find the probability that the time taken by Puffing Birdie to complete a full circuit is less than 25 minutes. Okay, let's see if we can shade that area in. Let's use orange. Oops, this one here. Alright, time taken is less than 25 minutes. Well, 25 minutes is probably right about there. So we're talking about this area in here. Okay, so we could take the integral of this function from t of this function here from 10 to 25 to find the probability that is less than 25 minutes. But as you can see, that's going to be a little bit annoying because this is a hybrid function. So let's think of another simpler way we can do this. So we could have worked it out that way, but we can also work it out this way, which would just be a lot simpler. If we're talking about this area here, we know that since it's a probability density function, the area under the entire thing equals 1. So that means this area here must be 1 minus, sorry, the area over here, which is what we're interested in, must be 1 minus this area here, because they must add together to give 1. So what we can say is 1 minus the integral of 25 to 30, aka this area here, of the function, which is our green line here. So it's 1 on 100 times 30 minus t dt. If you put that into your calculator, it says it wants an exact value. So if you put that into your calculator, you should get 7 on 8, which must mean that this area in here is 1/8. So let's just make that clear. So I'm saying this area in here we've just worked out is 7/8, which means this area in here is 1/8. But we wanted the area less than 25, so this is the one that we found by doing this 1 minus. One thing I forgot, which you definitely have to have, is the probability. You have to say what you're solving for, or what you've worked out. T less than 25 is equal to all that stuff. So just to sum up, we're saying probability t less than 25, the probability that it takes less than 25 minutes is 7/8. Alright, now we do some conditional probability. So it says find the probability t is less than or equal to 15 given that t is less than or equal to 25. Give the exact value. I find that a lot of people will struggle with conditional probability, so I've got a little diagram here. Let's think about what it's actually saying. So and how it changes the probability. So we're saying find the probability that t is less than or equal to 15 given that t is less than or equal to 25. So one way to illustrate how this changes the probability is we're saying think of all these values here. So the time it takes for the train to go around could be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, all the way up to 30. But what we've done by saying given that it's less than 25 is we've excluded all the numbers greater than 25. Now, I know that this is continuous probability, and this might be slightly confusing in the sense that it's these are discrete values like 26, 27, but just keep in mind I'm just trying to represent this information in a way where we can see, where we can visualize it. Obviously the values could be 26.5, 4, 3, 7, but we're just sort of doing this just to give us a bit of an idea of how a given that can constrain our probability. Anyway, so what we're saying is given that it's less than 25, so we can't have values of 26, 27, 28, 29 or 30, so we've got all these values in here. Find the probability that's less than 25. Well, that would be, sorry, less than 15. So that's all these ones here, less than or equal to 15. So hopefully the number of possibilities is reduced. Because we've gotten rid of these ones here, the number of possibilities is reduced. We can only go up to 25. So we're thinking, all right, what's the probability it takes these values here out of a possible amount of these values here? If you think to what probability is, remember it's the number of favorable outcomes divided by the possible outcomes. And what we've done is we've constrained the number of possible outcomes. I should write the word possible there. We've limited the amount of possible outcomes. So it's going to affect our probability. All right, let's see if we can attack the question now. So it's the probability t less than or equal to 15, 25. All right, using our conditional probability formula, it says that's the same thing as the probability t is less than or equal to 15 and probability t is less than or equal to 25 divided by the probability t is less than or equal to 25. Okay, so let's get this out of the way quickly. Alright, now what's the probability t is less than or equal to 15 and it's less than or equal to 25? Well, if it's less than 15 and less than 25, it's just less than 15. So we can say this simplifies down to 15 divided by the probability t is less than or equal to 25. Alright, looking back at our graph, less than 15. Well, that would be 15 would be about there. And since it's symmetrical, I haven't drawn it very symmetrically, but this area here, between 10 and 15, is equal to the area between 25 and 30. So we said before that this area here is 1/8, didn't we? So we know that this area here must be 1/8 as well, because it's completely symmetrical. So we know that t is less than or equal to 15 is 1/8, and t is less than or equal to 25. Well, we worked that out in the previous question. We said that that's 7/8. So you might be wondering, this one here says t less than or equal to 25, but the question above, or the question earlier, said t strictly less than 25. So I think this warrants maybe a discussion about discrete and continuous probability. The classic example that always gets given is versus foot length. What we've got here is two graphs of, the first one here is shoe size. Size, and this one here is foot length. Okay, your shoe size is discrete, so it can take specific values. It can be 9, or it can be 8, or it can be 7.5, or it can be 7, or it can be 15. Whatever it is, it's a discrete value, because the shoes only get made in discrete numbers. Your foot length, on the other hand, is a continuous random variable, because it can take any value on the number line. So, for example, your foot length could be, I don't know, whatever it is. I don't even know what average foot length would be. Like, let's make it up. Let's say 20 centimeters. I have no idea. 20.34796, blah, 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 blah. It goes on forever. It's continuous random variable if you wanted to get to increasing levels of specificity. But your shoe size can't do that. It can only have discrete values. So the point I really want to make here is, when we're talking about a continuous random variable, the probability of x being x being less than 9 is the same thing as the probability x is less than or equal to 9. Because remember, we're taking values all the way up to 8.9999463, whatever it is, and the calculator, when it does it, is going to basically work out the area under that curve up to, but not including, but it gets so close to it that we're essentially including it. That's how I think about it anyway. So when we're talking about continuous random variables, we can say that the probability that x is less than 9 is the same thing as the probability that x is less than or equal to 9. The key point you want to get away from it is that you essentially don't need greater than or equal to signs when you're talking about continuous random variables. They're unnecessary. When you're talking about your shoe size, for example, or a discrete random variable, it does matter, because the probability of a shoe size less than or equal to 9, all right, well, that's this one, this one, this one, this one, and this one. So let's write that down. So the probability x is less than or equal to 9 is those ones, but the probability x is strictly less than 9 is different. That's only this one here, this one here, this one here, this one here, this one here. So we can see for discrete probability it's different. So we need to have the difference in the sign. It's 6 circuits between 9 a.m. and noon. The management prefers Puffing Birdie to complete a circuit in less than 25 minutes. Find the probability, correct to 4 decimal places, that of the 6 circuits completed, that at least 4 of them take less than 25 minutes each. This is starting to sound like it might be binomially distributed. Let's see if we can test to see if it is. And this is a list of the things it must satisfy. The experiment consists of a number of n identical trials. Sounds good. There's 6 times it goes around, so that's our n amount of trials. Each trial results in one of 2 outcomes. Well, it either takes less than 25 minutes or it takes more than 25 minutes. So that's a success or a failure. The probability of success on a single trial P is constant for all trials. If we think back to before, the probability of success is 7/8. Its probability that the time it takes is less than 25 is 7/8. So that's a probability of success, P being 7/8. And thus the probability of a failure on a single trial is 1 minus P. Well, the probability of a failure will be 1/8 because we 1 minus 7/8. The trials are independent so that the outcome of any trial is not affected by the outcome of any previous trial. It doesn't say that explicitly, but we can assume that. So you'll get 1 mark if you write X is binomially distributed. There are 6 trials, so n amount of trials goes here, and we say 7/8 is the probability of success. Now, the probability X is greater than or equal to 4. If you put that in your calculator, you should get 0.97 9709, and it's correct to 4 decimal places. I said put it in your calculator. What do you put in your calculator? Well, you're doing a binomial CDF. Your lower bound is 4 and your upper bound is 6. For scheduling reasons, the management wants to know the time B minutes for which the probability of exactly 3 or 4 out of the 6 circuits completed, each taking less than B minutes, is maximized. Let the probability that T is less than B equal P. Let Q be the probability that exactly 3 or 4 circuits completed each take less than B minutes. Show that Q equals this. Alright, I can see how that's very confusing. So what we're going to say is, well, the first thing I'm going to say is exactly 3 or 4. So this is sort of the key part of the information. Probably exactly 3 or 4 circuits completed each take less than B minutes. Well, we can say the probability that T equals 3. No. Let's say the probability X equals 3, because that's the distribution we set up before. The probability X equals 3 is equal to, well, let's just set up a binomial distribution. It's 6 trials. We want 3 successes. The probability of success is P. We don't know what that is. To the power of 3, to the power, because we want that to happen 3 times. 1 minus P to the power of 6 minus 3, or n minus x, however you want to think about it. That gives us 3. Alright, let's do the other one. The probability x equals 4. When we say the probability x equals 4, he gets around, he completes the circuit 4 times in less than 25 minutes. So that would be, in this case, there's 6 trials still. We want 4 successes, so that we raise P to the power of 4. And then the amount of failures we get is 1 minus P to the power of, well, if we had 4 successes, it must mean we had 2 failures. Or another way to think about it is we had 6 minus 4 failures, so we had 2 failures. Okay. Now, what we can say is Q is the probability of that exactly 3 or 4. So we can say that Q is the sum of them. So Q is equal to the probability x equals 3 plus the probability x equals 4. Alright, let's see how we go with that. 6 choose 3, if you put that in your calculator, is 20. P cubed times 1 minus P cubed. Alright, plus 6 choose 4 is 15. So we have 15 P to the power of 4 times 1 minus P squared. Alright, if we simplify this down, we can see that we can actually take something out as a factor. So what it will be is we can take 5P cubed out as a factor. 5p cubed, we can see that, but we can also take 1 minus p squared out as a factor. So that's all been taken out as a factor, because we can see that in the first term here we have a 5p cubed, 1 minus p squared. We can take all that as a factor, and then we'll be left with, what will be left with? Well, we've taken 5p cubed out of 20p cubed, so we'll be left with 4, but we'll also be left with 1 lot of 1 minus p. So it'll be 4 times 1 minus p plus, well, we've taken this out as a 5p cubed times 1 minus p squared out of all this stuff here. That's going to leave us with a 3p, and that's it. It's going to leave us with a 3p because we've taken a 1 minus p squared out of 1 minus p squared. Alright, so this simplifies down to 3p, 5p, 1 minus p squared. Alright, this, I'll do this quickly, but it'll be 4, we multiply this in, is 4 minus 4p plus 3p. Well, that's simply 4 minus p. And then you do a big square, and you say QED or whatever, because you've successfully showed that Q is equal to 5p cubed times 1 minus p squared times 4 minus p. Alright, so this is where it gets pretty tricky to think about. So find the maximum value of Q and the value of P for which this occurs. So from the previous question, we see that we have some function Q. Q is a function of P. Now, let's just give this some context. From the start of the question, we know that P is the probability that the time taken is less than B minutes. So what that means here is, let's put it here. This is on our x-axis, so the probability that the time taken is less than some amount of minutes B is equal to P. Now that's confusing in itself. Along the other axis, we have Q. And Q is, what does it say? Is the probability that exactly 3 or 4 circuits completed each take less than B minutes. So what we can say is this is just a Q. Q is just a function of P. So for example, if the probability that T is less than B minutes is 0.4, so along here, if the probability that T is less than B minutes is 0.4, then the probability that exactly 3 or 4 circuits completed takes less than B minutes is, I don't know, what's that, approximately 0.4 as well. Now that's confusing, so let me say that again. If the probability that T is less than B minutes is 0.4, then the probability that exactly 3 or 4 circuits completed takes less than B minutes is approximately 0.4 in this case here. Alright, let's think about these endpoints here. At the point 1, what's happening there? Well, if it's guaranteed, so the probability is 1, that it's going to take less than B minutes, there is a 0 probability that exactly 3 or 4 take less than B minutes, because all of them must have taken less than B minutes. If there's a guaranteed probability that it takes less than B amount of minutes, then all of the trials that we did must have been less than B minutes. So the probability that exactly 3 or 4 of them took less than B minutes is 0, because all of them must have been less than B minutes. So I think that's very confusing, but you can sort of get away with this question without even really understanding what you're doing, as long as you know that P is a function of Q. Find the maximum value of Q. So we're asked to find this point here, and a value for which this occurs. Well, hopefully you realize you just have to differentiate. So Q dash, let Q dash of P equals 0 from your calculus. Hopefully you remember that. You'll get a couple of answers. You get P equals 0, 1, 2 plus root 2, and 2 minus root 2. Remember, these are all probabilities, so the one that we want is the one that, I don't know, is approximately around 0.6. Well, it's not 0, it's not 1, because that's at these points here. 2 plus root 2 would be greater than 1, and 2 so 2 minus root 2 is the only probability that sits strictly between 0 and 1. So anyway, my point now, what you do is you substitute that in back into the original function q. So q of 2 minus root 2 is equal to, and you put that in your calculator, you want to give it an exact answer, is 20 times 17 minus 12 root 2. So just to make it super clear, I'll just rewrite this part. So p equals 2 minus root 2, and q equals whatever that equals. Move on, let's just give this a little bit more context again. So what we've said, let's just use some numbers to make it more useful. This is approximately 0.59, and 2 minus root 2 is approximately 0.6-ish as well. Okay, so what we're going to say is when the probability that t is less than b minutes is equal to 2 minus root 2, which is approximately 0.6, let's say. So when the probability that t is less than b minutes is 0.6, the probability that exactly 3 or 4 of the trials took less than b minutes is 0.59. So we can say this point here is 2 minus root 2 and 0.59. All right, now this last question is confusing again. So find correct to 1 decimal place the value of b for which this maximum occurs. Okay, if we think back to the start of the problem, we had the probability graphed against the amount of time taken. This is our graph of that. Okay, now what we've said is we need approximately 2 minus root 2, which is approximately 0.6, of the area shaded in. So the probability that it's less than b amount of minutes, so this is b amount of minutes, has to be equal to 0.59, or 0.6, I should say, 0.6. So how can we work that out? Well, it's going to have to be some sort of integration. So what we're going to say is, unfortunately, this line here is to the right, and it would involve two functions. But so we can say that this, first of all, let's say this area here is 2 minus root 2, which means this area in here, let's do it in orange, must be, hopefully you know by now, 1 minus 2 minus root 2. Okay, so what we can do is we can use this one simply because we don't have to deal with two functions if we just take this part of it, and we can say that the integral from b up to 30, so to here, up to 30 of, what was the original function? It was 1 on 100. Let me quickly check. 30 minus t. 30 minus t dt is equal to 1 minus 2 minus root 2. Solving that for b gives us 20.9 approximately. So how you would solve that is you would put it in your calculator and solve for b, and that should give you an answer of this to 1 decimal place. What that means is when there's a maximum probability that if t is less than 20.9 seconds, there's a maximum probability that exactly 3 or 4 of the trials of the circuits took less than 20.9 seconds. So we found the maximum value. So we found the value of t for which if it's under 20.9 seconds has a maximum probability of also having exactly 3 or 4 trials that are under 20.9 seconds. So if you're confused, that's understandable, but see if you can work it out. And yeah, good luck.